Hello everyone, I am Shraddha Sulebhavikar from Sardar Patel Institute of Technology, along with my teammates Ishaan Sonar and Tejas Patil. So today we are going to present a MATLAB simulation project on the topic DTMF tone generation, that is dual tone multi-frequency tone generation. Let's begin with a quick introduction to what DTMF actually is. DTMF or dual tone multi-frequency is the technology used in traditional telephone keypads to represent the numbers we press as unique audio tones. Every time you press a key on a phone, like phi or hash, you actually generate two specific frequencies at the same time. One comes from a low frequency group and the other from a high frequency group. These pairs of tones allow telephone switching systems, modems, or even microcontrollers to easily recognize which key was pressed, even over an analog audio line. That's why it's often called touch tone dialing. DTMF has been widely used in telecommunication systems, remote controls, IVR, interactive voice response, menace, and even embedded control systems because it's simple, reliable, and easy to decode with basic electronics or signal processing. Now let's move to how we implemented this concept using MATLAB. We start with CLC, clear, and close all. These commands clear the workspace and ensure our program starts fresh each time it runs. Next, we define a standard phone keypad layout as a 4 by 3 matrix. This represents the familiar keypad on phones from 1 to 9 and symbols. Now we define the frequency pairs. Each row uses one of the low frequencies and each column uses one of the high frequencies. For example, phrasing 5 means combining 770 Hz and 1336 Hz. Next, we take input from the user. You can enter any key between 0 to 9, star, or hash. Then, we find which row and column this key belongs to. This identifies the correct pair of frequencies for that specific key. Finally, using those indices, we extract the DTMF frequencies that will form our tone. So up to this point, we have successfully linked the physical key press to its unique two-tone frequency pair. Next, my teammate Ishaan will show you how these frequencies are combined, played as sound, and then detected using FFT analysis.
Now that we have identified the low and high frequencies, we can generate the DTMF tone using MATLAB. Here, Fs is equal to 8000 Hz is the sampling rate, a standard value in telephony systems. The tone lasts for zero point 0.5 seconds. We add two sine waves, one low, one high, to get the combined DTMF tone. Now let's play it. You'll notice it's not a single pitch but two overlapping tones, exactly like what happens when you press a key on a real telephone. Next, to analyze this tone, we use the fast Fourier transform (FFT). This converts our time domain sound signal into frequency domain, showing which frequencies are present. We can visualize it with the code given below. When plotted, you will see two sharp peaks, one at the low frequency and one at the high, confirming that our tone contains exactly those two frequencies. To detect which key was pressed, we find the peaks closest to valid DTMF values. Finally, we match these detected frequencies to the keypad matrix. MATLAB prints. Now we'll see the output and hear the output tone. So, from a single key input, we generated a DTMF tone, analyzed it, and successfully detected it against using FFT. Now, my teammate Tejas will explain how this concept extends beyond MATLAB, its applications, future scope, and why DTMF based systems remain relevant in modern hardware and embedded projects.
Hi, myself Tejas, and I'll explain why this project has long term relevance and how it connects to future hardware and embedded systems. Even though DTMF started decades ago in telecommunication, its simplicity, reliability, and low bandwidth requirement make it useful even today, especially in embedded hardware and IoT applications. For example, microcontrollers like Arduino or STM32 can easily generate DTMF tones using PWM and detect them using ADC inputs. Robotics and remote control systems sometimes use DTMF to send controlled commands over GSM modules or radio channels because DTMF works through any audio link. In security systems or home automation, DTMF can allow users to control appliances by simply dialing from a phone. Our MATLAB model acts as a prototype, a digital proof of concept. Once verified, the same logic can be ported to C or Python and implemented on embedded boards. For detection, many systems use the Goertzel algorithm, which is computationally efficient for detecting specific tones, perfect for microcontrollers with limited resources. Now, let's talk about future longevity. DTMF may seem old, but it's still in use in IVR customer service lines, radio communication systems, GSM controlled devices, and audio based authentication or signaling systems. Because it uses simple analog frequencies, it's robust against digital transmission errors, making it a reliable fallback even in low bandwidth or noisy environments. Possible improvements include adding noise filtering to handle real world signals, using threshold detection on timing windows for precise decoding, and expanding the project into real time hardware using sound cards or IoT sensors. In short, this project bridges classic communication engineering and modern embedded design. We have demonstrated how a simple keypad input can turn can be turned into a signal, analyzed mathematically, and identified programmatically, forming the foundation for countless real-world applications. Thank you for watching our presentation on DTMF tone generation and detection in MATLAB. We hope this explanation helped you understand both the signal processing concept and its practical importance in hardware systems. Thank you.